All right, this is a 2006 question 4, and we're going to be looking at a two-sample confidence interval for means in this case. So patients with heart attack symptoms arrive at an emergency room either by ambulance or self-transportation provided by themselves, family, or friends. When a patient arrives at the emergency room, the time of arrival is recorded. The time when the patient's diagnostic treatment begins is also recorded. An administrator of a large hospital wanted to determine whether the mean wait time, time between arrival and diagnostic treatment for patients with heart attack symptoms, differs according to the mode of transportation. A random sample of 150 patients with heart attack symptoms who had reported to the emergency room was selected. For each patient, the mode of transportation and the wait time were recorded. Summary statistics for each mode of transportation are shown in the table below. So it turns out we have 77 were taken by ambulance, 73 brought themselves. This is an X, so these are my sample means. These are my sample standard deviations. And because I'm working with sample standard deviations, we know that this is going to be some sort of T. So use a 99% confidence interval to estimate the difference between the mean wait times for ambulance transportation and self-transportation patients at this emergency room. So I need to start off by defining my parameters. And I started off by saying, let mu A, or could it be mu 1, equal the true population mean wait times for arriving by ambulance, and mu S equals the true population mean wait time for arriving by self, family, or friends. You don't have to state the null and alternative, but I tend to do that because it just keeps me thinking. So in this case, we're assuming that they're equal, but because the confidence interval is always a two-tailed test, because it's always a two-tailed test, my hypothesis statement would be not equal if I wrote it. Not required to have it, it's not necessary, but it helps me, myself, when I'm doing my work, but certainly not required. So random sample for both means of transportation were taken. This is given. And the key word there is both. The two samples are independent. It's unlikely that the number of patients that choose to use the ambulance is likely to impact the number arriving themselves and vice versa. So we have independence. N is less than 10%. Reasonable to assume that there are more than 770 heart attack victims taken to the hospital by ambulance, and reasonable to assume that there are more than 730 heart attack victims taken by family or friends. So the N is less than 10% for both. They also give a sample size, and N is greater than 30 for both samples. And so the distribution of the mean is approximately normal by central limit theorem. So that's good. I don't need to draw my graph. So there's my normality. So then I name my test. What am I running? Two sample T interval for means, or two sample T confidence interval if you prefer. Here's my formula that I'm going to go ahead and cross out. But I use that to plug in my values. So what values am I plugging in? Not going to quite fit, so let me see if I can make an adjustment here. There we go. All right, so the values are, as I have my 6.04 minus 8.3. Now this is ambulance, and this is self. And there are my standard deviations, etc. But how do I get my T-star? Well, that's a good question, and it's a little bit backwards. And the other question you should probably ask is, how do I get that off of degrees of freedom? Well, at this point, what I do is I go ahead and run the test first. So stat test, two sample T interval, and I start plugging in my statistics, which are 6.04, 8.3, oops, try that again. 6.04, 8.3, 4.3. I'm plugging that in wrong. 4.3. Then the mean for that has a sample size of 77. Then I have a mean of 8.3, a standard deviation of 5.16, and a sample size of 73. And they want a 99% confidence interval. So I'm going to plug in 0.99. We never pool. And I go ahead and calculate. And I get a bunch of information that I need to write down. All right, so first off, I get my lower bound and my upper bound. So there's my lower and upper bound for my interval. I also get my degrees of freedom. So I need to note that down because I'm going to need that here in just a moment. And I can verify all the data that I plugged in to make sure it matches what I have in. So now I need to go back and get that T star. So to get that T star, second vars, inverse T, 1 minus 0.99 divided by 2 in degrees of freedom is about 140.37. And I end up getting 2.6113. So that's where that is, and I have my interval. So now that I have that and my interval, I can go ahead with my statement and say we are 99% confident the true population difference in means. And notice that's what we did. We subtracted two means, so we had difference in means, or a difference in mean wait times for treatment ambulance minus self lies within this interval. In repeated sampling, we expect to capture the true population difference in mean wait times ambulance minus self 99% of the time. And finally, part B. Based on this confidence interval, based only on this confidence interval, do you think the difference in mean wait times is statistically significant? Well, I notice that 0 is not in the interval. If 0 is in the interval, it's not statistically significant. But if it is in the interval, it is. If it's not in the interval, it's statistically significant. So in this case, it's not contained within the interval, which indicates the difference of wait times to the hospital is significant. Matter of fact, because it's negative, we can say, well, that means this number is smaller, which means the ambulance time is less than the self time. So we can basically determine that statistically significant that ambulance will get us service faster than self, according to this study. That's not what I meant to do. So share. I need to stop the recording.